Welcome back to this lesson, Basic Cache Optimization Techniques. In this lesson, I will discuss some basic cache optimization techniques. But first, we need to define some cache performance metrics. What do we want to improve? The first cache performance metric is the hit rate. The hit rate is given by the number of cache hits divided by the number of cache accesses. Similarly, the miss rate is defined as the number of cache misses divided by the number of cache accesses, which by definition equals 1 minus the hit rate. Unfortunately, both these cache metrics do not factor in the cost for a hit and the cost of a miss. Therefore, the hit time will be used to define the time for a hit, and the miss penalty will define the extra cost of a miss. This gives us a very important equation called the average memory access time, or AMAT. The AMAT is given by the hit time plus the miss rate times the miss penalty. That's the goal. That's what we want to optimize in this lesson. To understand what causes cache misses, where cache misses come from, we categorize them into 3 different types of cache misses. For this, we use a famous model called the 3 C's, because every cache miss is classified as a cache miss that starts with the letter C. The first one are compulsory misses, also called cold start misses. These are misses that are caused by the fact that the first access, because we fetch data on demand, the first access to a block is always a miss. We can measure, in a simulator, we can measure the compulsory misses by counting the number of misses in a hypothetical cache of infinite size. The second type of cache misses are capacity misses. Because the cache cannot contain all blocks that are needed now and in the near future, capacity misses will occur because blocks will be discarded and later brought to the cache again, later retrieved. You can measure those in a simulator by counting the number of misses in a fully associative cache with optimal replacement. Then there are conflict misses. These are misses that occur because several blocks map to the same cache block that map to the same set. They're also called collision misses because the cache blocks collide on the same set. And basically all other misses can be classified as conflict misses. So how can we improve cache performance? Here's again the equation for the average memory access time given by the hit time plus the miss rate times the miss penalty. First, how do we reduce the hit time? Right? We can reduce the hit time by using relatively small and simple caches. Right? Then, how can we reduce the miss rate? We can first reduce the miss rate by increasing the block size. This exploits spatial locality better than when we use a block size of only 1 word. Or we can increase the number of ways the associativity of the cache. Or we can build bigger caches, we can use larger caches, but this usually has a negative influence on the hit time. This shows, and this is very often the case in computer engineering, computer architecture, that we need to make a trade-off. And the third way to improve the average memory access time is to reduce the miss penalty. And I will discuss in this lesson 2 techniques to do so. First, employing multi-level caches, and second, to give priority to read misses over writes. First, let's look at larger blocks, larger block sizes, because blocks of 1 word do not fully exploit spatial locality. Why would it make sense to use larger blocks? Well, it's simply more efficient to transfer n words at once than to transfer n single words. The typical block size for the first level cache, the level 1 or L1 cache, is, for example, 32 bytes, 8 words, or 64 bytes, 16 words in MIPS terminology. A larger block size reduces the miss rate because now we better exploit spatial locality, but it increases the miss penalty. Let me show you an example to illustrate this. I make the following assumptions. The hit time is always 1 clock cycle. The miss penalty is 10 plus the number of words per block clock cycles, and the miss rate is summarized in this table here. When we increase the block size from 4 byte to 8 byte, the miss rate reduces from 10% to 6%, etc., etc., etc. Every time the miss rate reduces a little bit up to using a very large cache block size of 128 bytes. But now the question is, which block size has the smallest average memory access time? To calculate that, we need to calculate also the miss penalty. It's 11 for 4 bytes, 12 for 8 bytes, and so on, up to 42 for 128 bytes, because 128 bytes corresponds to, let me calculate, 16 words. No, 32 words. Yes, exactly, that gives 42. Now we have everything in place to compute the average memory access time given by the hit time plus the miss rate times the miss penalty. And if we do that on our calculator, we see the average memory access time for 4 byte blocks is 2.1. It's 1.72 for 8 byte blocks. But the optimal point is, the optimal trade-off point is 1.54, which is achieved for 32 byte blocks. Now I want to say what an associative cache is, but before I do that, I want to motivate them. Let's consider an example from before that computes the dot product, a simple loop that computes the dot product of two vectors A and B. Here we show how the arrays A and B are allocated in memory. Both of them are, we assume both of them are power of 2. The size is a power of 2 and the size is a multiple of the cache size, right? They're consecutively allocated, and that means that every access to A and B in this loop generates a miss, right? Because A0 and B0 map to the same cache block in a direct map cache. Similarly, when we need A1, it has been replaced by B0 because also A1 maps to that cache block. What can we do to solve this problem? The solution is to allow more flexible placement of blocks, and that motivates associative caches. This slide here shows 4 possible organizations of a cache with 4 blocks. At the top left, we have the direct map cache. In this case, there is 1 block per set, so the number of set equals the number of blocks, and we have 4 blocks, so we have 4 sets. Therefore, it is also called a one-way set associative cache. We can also say, no, we don't have 4 sets, we have 2 sets. This brings us to a two-way set associative cache. We have 2 sets, and each of these 2, the tag and data, are the ways. So our associativity is 2. Or we can use a 4-way set associative cache. In this case, because we have only 4 blocks, it's also called a fully associative cache, meaning we have only 1 set and the block can be placed in any one of these ways. In the last lesson, I showed you some equations for a direct map caches. These equations relatively easy translate to equations for a set associative cache. The block address is as before given by the byte address integer divided by the number of bytes per block. The cache index is given by the block address modulo the number of sets. If we have a direct map cache, the number of sets is equal to the number of blocks, and block address modulo the number of blocks was the equation we use for a direct map cache. In a fully associative cache, the number of sets is 1. That means the cache index is always 0, and therefore usually we don't mention it anymore. And the tag is now given by block address divided by the number of sets. This gives us another equation. The cache size, meaning the cache capacity, is given by the number of sets, which is the number of lines in our cache, times the number of ways, which is kind of the number of data columns we find in the cache, also 2 in this example of a 4 block cache, times the number of bytes per block. This picture here, this figure here, shows a 4-way set associative cache. Right? To find if a block is contained in this cache, we index the cache using some bits from the requested address. We use 8-bit, that means we have 2 to the power of 8, 256 sets. For each of these cache blocks has a tag. And in parallel, we compare the tag to the tag of the requested memory block up here. If either of them and only one of them can match, if either of them match and the valid bit is set, then we have a hit indicated by this large OR gate here. And this multiplexer is needed to select the right word, the right block from the 4 that were given to us. Some questions regarding this figure. How can we see what the block size is? Well, the block size, the last 2 bits are not used to index the cache. That indicates that the block size is 2 to the power of 2 is 4 byte equals 1 word. And what is the size of this cache? Which is equal to the number of sets times the number of ways times the size of 1 block. One more time, this cache capacity equation. If we say cache size, we usually mean how much data can the cache contain. So it is about the cache capacity, right? A lot of questions ask me, do I need to memorize this equation by heart? My answer is no. No, but you should be able to reproduce it. And to give them a hint how to reproduce, I always show this figure. You know what the size of this table is, right? It shows that the number of sets is 8, the number of rows. The number of ways is 4, the number of columns. And the block size equals the bytes per block. So the entire size of this matrix is given by the number of sets times the number of ways, also called associativity of the cache, times the bytes per block. Here's an example for the instruction cache of the Intel Core i7, which is a very recent processor from Intel. Its size is 32 kilobyte. It has a block size of 64 bytes. The associativity, or the number of ways, is 4. It's a 4-way set associative. And the address length is 48-bit. Now the question is, how long is the index in bits? And how long is the tag in bits? Given all the information I told you, these questions should be answered relatively easy. First, we know the cache size equation, number of sets times the number of ways times the bytes per block. The cache size is given, the number of ways is given, 4, because it's 4-way set associative, and the number of bytes per block is given because it's 64, it's the block size. So we can calculate this, we can substitute these numbers in this equation. We can divide 32 kilobyte by 4 times 64. This gives us 128, which equals 2 to the power of 7. That means the length of the index must be 7 bits. Regarding the second question, how long is the tag in bits? We must know this equation. The tag length is given by the address length minus the length of the index minus the offset, the block offset length. All this information is available somehow in all these equations. The block size is 64 and 2 to the power of the block offset length must be the block size, so the block offset length equals 6. We know the address length is given here as 48 bit, so the tag length is 48 minus 7 bits for the index minus 6 bits for the block offset equals 35. This brings us to a next question. Which block will be replaced if all blocks in a set are occupied? I didn't bring up this question when the last lesson when I discussed direct map caches, because basically there is no choice for a direct map cache. If a block maps to the same cache block as another in a set, then we need to replace the block that is already present. Now, if we have set associative caches, we can replace any of the blocks in the set. What are usual replacement algorithms for this? One possibility is to replace a random block in the set, the random strategy. Another possibility is first in, first out, FIFO, which tells us that we should replace the block that entered the cache first, which has been in the cache for the longest time. And what is very often used is LRU, or an abbreviation of LRU. LRU tells us that we should replace the block that has not been accessed for the longest time. And we have the optimal algorithm, which tells us to replace the block that will not be used for the longest time. Why don't we implement the optimal algorithm in our in our current computer system? Well, we need to have knowledge of the future. So the optimal algorithm is only a good indication of how far we can get if we have perfect knowledge of the future. It's a limit on the performance we can get. Let's get back to our original question: how do we improve the average memory access time? Right? I talked about larger block size, I talked about higher associativity, which are both aimed at reducing the miss rate. I will very briefly now talk about reducing the hit time by using small and simple caches, and techniques to reduce the miss penalty by using multi-level caches and by giving priority to read misses over writes. First, small and simple caches. Why should we use small and simple caches? This figure here shows the access time of a cache for different associativity and for different cache sizes. Here at the bottom we have different cache sizes going from 16 kilobyte to 30 kilobyte up to 256 kilobyte, and on the vertical axis we show the access time in picoseconds, right? These results have been obtained using a cache simulator called Cacti. We see in general that increasing the cache size increases the cache access time. Not always, but in most cases. We also see that increasing the associativity also increases the cache access time. So as a rule of thumb, we can say larger caches have larger hit time, and higher associativity also has higher hit time. Here's another technique that I would classify as a simple cache optimization technique. The use of a split cache. In one cycle of our canonical pipeline, 5-state pipeline, we need to fetch an instruction in the instruction fetch state, and we need to read the data from cache for a load or store data to a cache, store. If we have only one cache, one cache that is unified, the cache must have 2 read ports and 1 write port. Unfortunately, multi-ported caches are complexer and therefore slower, larger, and more power consuming than a single-ported cache. For that reason, it's better to use a split cache. That means we have one cache for instructions, typically called the instruction cache, and one cache for data, dcache or $. Now, in one cycle, look here, we can fetch an instruction and we can access the data both using a single ported cache. This brings us to the first technique that I will discuss to reduce the miss penalty. The first one is to employ a multi-level cache. We want to reduce the miss penalty by multiplying not one, but several cache levels. First, our level cache should be small and fast enough to have a hit time of about, preferably 1, sometimes 2, up to 3 clock cycles. The level 2 cache can then be much larger and it will also be slower, but it's still much faster than main memory. Typical L2 hit times are 10 to 20 clock cycles, but this is still much faster than the latency to main memory, which is in the order of 100 to 500 processor clock cycles. High-end processors, high-performance processors even have a level 3 cache. Brings us to the next question. How do we measure the performance of a multi-level cache? I will illustrate it using an example. Here are my assumptions. I assume that the base cycles per instruction, base CPI, is 1.0 under the assumption that all accesses hit in the level 1 cache. Furthermore, the frequency of our CPU is 4 GHz, meaning a cycle time of 0.25 nanoseconds or 250 picoseconds. Also, the main memory latency is 100 nanoseconds, corresponding to 400 processor clock cycles. And the miss rate in L1, the combined miss rate for both instructions and data, I assume is 2%, which is a reasonable assumption. Then, if we only have an L1 cache, the CPI is given by the base CPI times the miss rate of the L1 times the miss penalty of L1, which is the access time, the main memory latency. If we substitute these numbers, we get 1.0, the base CPI, plus 2%, the miss rate in L1, times 400 equals a CPI of 9.0. Now I'm going to add a level 2 cache. It has, that's the assumption, a hit time of 5 nanoseconds, which is substantial, which is 20 processor cycles. The miss rate is also quite high of L2 and is 25%, which is the number of misses in the level 2 cache divided by the number of accesses to the level 2 cache. Why is it relatively high? The answer is because most accesses will not pass by the level 1 cache. The level 1 cache has exploited most of the locality. Here I summarize again the performance if we only have a level 1 cache and now we add a level 2 cache. Then the CPI is given by the base CPI plus the miss rate of L1 times the miss penalty of L1. The miss penalty of L1 is now not the latency to main memory, but it's the hit time of L2 plus the miss rate of L2 times the miss penalty of L2. If we now substitute these numbers, we see that the CPI is 1.0 plus 2% times 20, the hit time for the level 1, times 25%, the miss rate of level 2 times 400, which is the miss penalty of L2, which is the main memory latency, and this gives us an average CPI of 3.4, and we see that the processor with an L2 cache is faster by a factor of 2.6. This brings me to the last fundamental cache question. What happens when we write data? First, let's consider what happens on a write hit. Do we write the new data only to cache or also write to memory? The answer is both have been implemented, both are possible and both have been implemented. In a write through cache, the new data is written both to cache and to memory. The advantage of this approach is that cache and memory are consistent at any time. They contain the same data. A disadvantage is that there are many writes to memory. Every new data word is written to memory. Another technique is a write back cache. That means the new data is only written to cache and only to memory when the block is replaced. The advantage of that is that we have fewer writes to memory because several writes to the same cache block, because usually there are several writes to the same cache block before it is replaced. The disadvantage is, however, that now cache and memory can be inconsistent. They may contain different values, different data for the same word. This brings me to an optimization for a write-through cache. This optimization is called the write buffer. When we read data from memory or from cache, then we want to return the data as soon as possible to the CPU so that the CPU can continue with computing. The writes, on the other hand, are not on the critical path. They can happen in the background. The write buffer stores data until they are written back to memory. Right? The CPU continues and only stalls when the write buffer is full. This is illustrated here in this figure. When we write the cache as well as memory, we write the new data into the cache, if we had a write hit, and into the write buffer, and the write buffer in the background writes the new data back to main memory. This brings me to an optimization for a write back cache. We only need to write back a cache block if it has been written the last time it has been fetched from the main memory. Therefore, we add one bit to every cache block, and that bit indicates if the data has been written, modified, but typically this bit is called the dirty bit. It indicates that data is dirty, that it has been modified. Write back caches typically also have a write buffer, but for replaced dirty blocks. So instead of waiting for the dirty block to be written back to main memory, we get the new block and the CPU can continue while the dirty block is written back to memory in the background. For this reason, the write buffer for write back caches is sometimes also called write back buffer. There's another subtle difference between a write through and a write back cache, and that is that the write through cache can be written while we are doing the tag comparison. Why? Because memory or the write buffer has the most recent up-to-date copy of that block. So if it was a cache miss, it doesn't matter because we still have the cache block, a valid copy of the cache block in memory. For write back caches, we cannot do the same because that may be the only copy, the right copy, that is left in the system. This brings us to one more question regarding caches, and that is what happens on a write miss. We write data, but the data is not present in the cache. Again, there are two approaches. The first one is to write allocate or fetch on write. That means we first load the block in cache on a write miss, and then we do exactly the same as for a write hit. The other technique, as the name says, is no write allocate or write around. That means that the block is modified in memory, but it's not loaded into the cache. So in general, the write policy is an element of the Cartesian product of write through and write back times write allocate and no write allocate. Although all combinations are in principle possible, write back caches generally use write allocate, whereas write through caches often use no write allocate. Now I have everything in place to discuss giving the last basic cache optimization techniques, giving read misses priority over writes. As I said before, read misses must be handled as soon as possible because the execution units are hungry, they want to eat, they stall waiting for data. Writes, on the other hand, can happen in the background. But there's a rule that we must maintain, an order we must maintain, and that's the memory order. The memory order tells us that a load should return the value written by the most recent store to that very same address. That means that on a read miss, we must either drain the write buffer or check the write buffer first. Here I have a small demo to illustrate this. We have the variable a in main memory and it contains the value 9. Now the CPU writes a new value 7 to the cache. It doesn't wait until the write is completed, so it writes a becomes 7 into the write buffer. Now the CPU wants to load a. If we now give the load of a, the read of a, priority over write, it would go to the cache or it would go to memory and fetch the wrong value, namely the old value, the value 9. This is not allowed, we must maintain memory order, so the read of a should check the write buffer first and return the value 7. If the data, the newest data, is still in the write buffer. Thank you for your attention. Hope to see you back in the next lesson.